So ladies and gentlemen, good morning to America, good afternoon in Europe, good evening in Australia. My name is Pavel Bauer. I am from Delft University of Technology, and I will host this keynote as a chair. Welcome to the second keynote with a very timely topic, energy storage and overview of research. And our keynote speaker is Dr. Claudio Cañizares. Professor Cañizares is a professor at Hydro One Endowed Chair at the Faculty of Department of Electrical Engineering, Computer Science of the University of Waterloo in Canada. He has been there since 1993. His highly cited research focuses on modeling, simulation, computation, stability, control, and optimization of power and energy systems. He is the IEEE Transaction Smart Grid Editor-in-Chief and Fellow of the IEEE, Fellow of the Royal Society of Canada, and Fellow of the Canadian Academy of Engineering. He is also recipient of the 2017 IEEE PES Outstanding Power Engineering Educator Award and 2016 IEEE Canada Electric Power Medal and multiple awards and recognitions from PES technical committees. So Claudio, floor is yours. We expect presentation of 45 minutes, and after that we have questions of 15 minutes approximately. Claudio, please, your keynote.
Okay, can you hear me now? Hello? I guess we can hear me.
Yes.
Okay, sorry. Sorry about that. Yeah, I had a connection problem here. Thank you, Pavel. I appreciate the introduction. It's a pleasure to be here. Thank you for the invitation. We've been collaborating with Pavel's group and in general the project that he's co-leading is part of for a while, and it's under that aegis that I'm participating in the meeting. So it's a pleasure to be here. So just to move on. This is the title of my presentation, which basically involves the research of all these fellows, students, and postdoctoral fellows that are listed here. I'm going to briefly introduce my university so you know where I come from. University of Waterloo, which is basically 150 kilometers due west of Toronto. It's a university with basically a technical university. Focus mostly on science, math, and engineering. So we have about 40,000 students, including international students, and is co-programming. Basically, the students study and work every other term. We have several institutes and faculties which I'll discuss, but the institutes I belong to, which is the Waterloo Institute for Sustainable Energy. This is where the main institute I belong to, and these are the faculties in engineering, which is one of the major engineering faculties in Canada, and I belong to the Electrical and Computer Engineering Department. So, which is a 100% co-op program. We have 90 plus faculty members, multiple chairs, I'm one of them, and multiple fellowships. And we have about 2,500 students, and we are part of all these programs. These two belong to our to our department, and these are programs that we share with other departments and faculties included. And as I mentioned, we are fully a co-program. These are the groups that we have. We have about 300 PhD students, mostly PhD students, and about half of them are masters. And now we have a very active master engineering program in which we are moving our program towards, since MAC's research is very limited, so we are trying to focus on an MH program. And I belong to the Power Engineering, Power and Energy Systems group. These are the various labs that the department run, and our program is one of the few, at least in North America, that has a high voltage engineering lab. Regarding the Power Engineering, Power and Energy Systems program, we basically cover a gamut of we are very well known in North America, and we are 8 professors, and we have a gamut of all these programs. So see, these are the areas that basically each one of us covers. I mostly focus on power systems, I'll describe that, but we cover distribution systems, markets, high voltage, power electronics, protections markets. So it's very, very varied program in 5 of our IEEE fellows. Okay, we have multiple collaborations, and in my group, I focus on different aspects of power systems, smart grids, and the editor-in-chief of the IEEE transactions on smart grid. So in this area, I focus in different aspects of smart grids. I've worked significantly with renewable energy sources integration aspects, electric vehicles. I've done quite a bit of work. Microgrids, I've been working on that for the last decade or so. Quite a bit of work on that area of facts, and energy storage, which is going to be the focus of my presentation today. So to move on to the energy storage presentation, which is what I'm going to be describing today, let me start by recognizing the our collaborations, our funding from mainly NSERC, National Science, Engineering and Research Council of Canada, and the Ontario Centres of Excellence, which is basically granting agencies, government granting agencies. And we also have collaborated with multiple partners, government and private, EnerStore, Compass Minerals, the Ontario Power Generation, and the ISO. This is one of our main partners in our work in energy storage, which is making our work real and applied. And we also collaborated with the Karlsruhe Institute of Technology, and that's for several years now. Now, this is the outline of my presentation after this brief introduction of where I come from and what my group works on. And I'm going to be covering the following aspects. First, I'll give you an overview of energy storage. Then I'll give you the research objectives of my group, which is going to be the focus of this presentation, the work we do. And we work in different aspects of energy storage, and mostly modeling, simulation, stability control, and operations. And we have worked on flywheel energy storage, compressed energy storage, battery energy storage, regulation services of these storage systems, and behind the meter CAS. So we looked also at basically lower power applications. We also have done quite a bit of work in thermal energy storage and the integration of CAS, compressed air energy storage, to electricity markets, which is one of the works we are doing right now. And on a side, or related to this, we have been working on sort of a fax application applied to energy storage, hybrid power flow control, which is a different power electronic system that we have helped develop and analyze. So to give you an overview of energy storage, what is motivating all of this, as we all know, is the integration of wind and solar resources, variable sources in the grid. And in the case of Ontario in particular, there's been a significant increment of these resources in the province. Although Canada in general is basically a hydro, as a country, a hydro focus power system. In the case of Ontario, we're mostly nuclear. But a good share of the resources of the renewable resources now is becoming is being added to the system is wind and solar, mostly wind, with the intention of trying to get rid of gas in the future. We moved to a coal system, which disappeared in 2014, and now is mostly nuclear and hydro. And as the reasonable share of wind, not as much as other countries like Netherlands, Denmark, Germany, for example, but is steadily growing. Now, these variable, non-dispatchable renewable energy sources is introducing multiple challenges, particularly for frequency stability. That's one of the main concerns in the integration and addition of renewable energy sources. And considering that these very quickly, from a point of view of frequency regulation, conventional generation resources are limited. So in other words, they cannot really compensate for the variable, fast variable rates of these energy sources. So what is coming to a fore is the energy storage technologies, which are trying to basically present an alternative, a way of attenuating this intermittency, fast intermittency of variable energy sources. Now, what are the energy storage technologies? You have a list of here. There are mechanical, electromechanical, and electrical. We also have thermal and chemical. Okay, from the point of view of electrochemical, pardon me, not electromechanical, electrochemical, and we have focused in particularly all of this. And the ones highlighted in green are typical applications in microgrids. Now, depending on the duration and the frequency of operation of these units, you have different applications. For example, we have focused on compressed energy storage, which we have used for multiple, can be used for multiple applications, from a few seconds to minutes. Battery energy storage, on the other hand, are very good for different applications like frequency regulation, power quality, energy shifting, and in some cases, grid forming applications. Okay. Now, these are the technologies from the point of view of energy storage. So you have battery energy storage, which is basically electrochemical reaction. You have variations of these, which are basically based on flow batteries. You have electromechanical systems, which are flywheels. You have also hydrogen type of systems in which you have electrolyzers and a fuel cell, and you have different applications of thermal energy storage. Okay. The ones we have worked on specifically have been for heating, cooling, and ground source heat pumps. Now, in the case of Ontario in particular, where I come from, there's a program that has been developed since 2014. Was introduced in 2014 and is very active. The introduction of 50 megawatts of energy storage power. And as you can see here, these are the different technologies: battery, flywheels, flow batteries, CAS, an interesting system that has been developed, adiabatic, interesting decouple charging and discharging system that is now in commission. Hydrogen systems, thermal systems as well, and underwater compressed air energy storage. Now, from the point of view of energy storage in the system, we have a significant amount of pumped hydro. This is where the others come in. These are the technologies. So we have not worked with pumped hydro. These are well-known old technology, but we have a significant amount of pumped hydro in the Niagara Niagara region. Now, with respect to the research objectives that we have we're mostly focused on the following three aspects: developing energy storage models, which is what I'm going to be talking about, considering operational features and constraints, the integration of these models, okay, into existing mathematical models and simulation tools, okay, with the intention of do operation analysis and control of power systems. Okay. And finally, the contribution and impact of energy storage into the performance and operation of power systems. So these are the three main objectives of our work. This is what we have been working on, and let me describe exactly what we have done. So part of our work has focused on flywheels, which are basically systems in which you have a mechanical system with a large mass, a flywheel, motor, and an interface, an electronic interface, and basically which is a AC link, so based on voltage source converters, which are described here for the interconnection of the system. And there's an example here in Ontario, a flywheel in Mindo, in which I already described, of a few megawatts, which is providing frequency regulation services for the province. Okay? And one of the advantages of frequency regulation of these flywheels is fast response and high flexibility. These are applications for power, frequency regulation, power applications, not for energy. Okay? So that's the particular characteristics of these systems. Okay? And you basically are based on transformer rotational kinetic energy, this mass here, that energy into services for the grid. Okay? You can also provide reactive power support, as we'll see in a second. Why? Because you have voltage source converters that allow you to also provide reactive power services. Okay? And the idea or the applications of this, or the characteristics of this, is fast charge discharge rates, high power energy density, long life, and very environmentally friendly. Now, there's a paper that we published a while ago in the proceedings of the general meeting in 2018, in which we describe the different aspects of these systems. And we focus on the machine and flywheel model, the voltage source converter model, which is an average model, the voltage source controls, which was basically one of the main focus of this paper. So representing the controls of the voltage source converter on the machine side and on the grid side, and the application to speed frequency control. So we were basically focused on providing frequency regulation services to the grid. And we worked with this example in which we compared against having no compensation when you have a wind energy system, providing variable power. This is from a previous paper in which basically they studied the application of the services of StatComs and flywheels. We compared that with an SBC system and the flywheel system and how they compare. And basically, we looked at what happens when you have significant wind speed variations. This is the variation power, the impact on the frequency, as you can see. Maybe I should be more specific here quickly because we don't have a lot of time, but I'm looking for the eraser here. Just give me a second. So this is the impact on frequency in the system, and this is the impact of when you have a flywheel, how the frequency is regulated in the system, okay? And it can also provide, as you can see here, voltage regulation services. Then we can work in compressed energy storage systems, the large ones, in which you basically have a system in which you have, in our case, we have looked at charging and discharging phases, separate charging and discharging phases, which is the way this compressed energy storage system technologies has developed, but the direction is going into, which is a generator and a motor in one side connected to a turbine, and the other side connected to a compressor, and the other side connected to a turbine. Okay, and then you have, as in the case of Southern Ontario, you have cavern storage. Why cavern? Because we have salt mines, which are ideal. These salt mines that once they have been spent, ideal storage. Cavern storage availability for this system. So this is exactly what has happened in the case of Ontario. So the actual plants that exist, you have one in Huntorf in Germany and one in Macintosh, which are the only ones that are active and exist at this point, which are significant size systems. Okay. Now the interesting thing about this is that this technology, at least in Ontario and these areas in which you have these salt mine areas, they are ideally positioned for these systems. Now you gotta consider that this technology is not fully 100% clean. Why? Because you have a gas system, it's a diabatic system. You need to heat up the air to reach the pressures you require to move the generator. Okay. Now, in an adiabatic system, you basically use the heat from the compression stage to replace the gas. And there's now a plant in Ontario which is basically doing exactly that with this technology of separate charging and discharging phases. Okay. And this is the system we have developed, the model in the system describing all these papers that are here, and all the different phases, as you can see here, compressor phases, turbine phases that allow you to. Okay, I'm trying to see, getting some blinking lights here. Now, and by the way, we have developed the detailed model of all these systems. You have preheaters, systems that allow you to take heat away or add heat to the system. And it has very different phases, recuperators and aftercoolers, intercoolers on the system. Now, we have applied this to frequency regulation. So we have basically looked at the frequency regulation models, as you can see here, the standard frequency regulation models, which is a first order type of models, in which we're looking at basically comparing the steam generator with having a CAS system on both phases, generation and load. Okay, and comparing all these different systems against each other, and that's exactly what you have here. So what you have here is the system where you have a gas turbine, okay, as indicated here, which it provides certain frequency regulation, but it falls outside the bandwidth set by the ISO in Ontario. Okay. The gas turbine is not fast enough, is not able to provide the required services. Whereas if you introduce a CAS that charges only discharging to provide that regulation, like a gas turbine, you get better performance because of the fact that you have pre-compressed air that allows it to provide better, faster services in the system, as opposed to a gas turbine that basically sucks air from the system and compresses, okay, through the turbine system. Now, in the case of charging and discharging, you get even a better performance, as you can see here, which is the blue line here. I guess is case 3, in which you basically have the performance of the system. And the case 3 that appears here is the detailed model versus the simplified model we have developed, which basically from this perspective performs exactly the same way. And then we have applied these to the provision of services in an actual system. So we have looked at a relatively small model in which we are comparing the CAS versus a gas turbine and studying different cases of operation. And you can see here that the best, I guess the case 9, when you have charging and discharging mode, is the best performance of your system, which is the performance you see here from the point of view of transient stability and from the point of view of frequency regulation, which is over here. And as you can see, the performance is quite good. Then we have looked at battery energy storage. Remember that I'm just providing an overview here of different technologies and applications, in which basically we have been focusing on the aspects of the fact that battery energy storage, the most likely interface with the system would be through distribution systems. Although there are large systems that are being studied and developed in practice, what you would expect in the future is to have at the distribution system level, multiple energy storage sources, battery energy storage sources that will basically be interacting, would be able to provide energy service in the system. So the idea was, or the idea of our work has been how you harness these resources to basically provide services for the transmission system. Okay? So we have been developing aggregated. And this is the basic technology you see here in battery energy storage. You have your battery, a DC boost converter, a voltage source converter through a DC link, and your filter, and all the different controls that you are able to provide. One is following the grid, and another one is basically providing your own frequency regulation services. That would be basically is trying to remember what that is, whether you provide an angle reference or a PLL. So you follow the grid or you form a grid. And we have looked at average models of these, detailed models and average models of this. And basically that's what we did first. It's all described in these different papers that are here. If you're interested in finding more details about it, I believe you have access to these slides. And we have the first stage of our modeling was to look at the very detailed model with the different aspects, controls, etc., interactions with the grid, and the detail versus an average model, and the limitations of the average model. We have seen that in certain conditions, the switching that does make a difference from the point of view of stability in the system. And the applications to a grid. So this is basically an aggregated model of the system. We assume that we have located a battery energy storage in the system. We are in the process of publishing our work on aggregated models. And I guess that's still in the works. But basically, the intention is that these services are going to be provided, that the system can provide, are manifold. And basically what you have here is an impact on frequency, voltage, power in the system, where the system is able to provide the following services. So you can provide frequency regulation services, as you can see here, very adequate, when we can compare versus different type of models, okay? The second conclusion is that you can provide voltage regulation services as well, and also power oscillation services. So, which improve basically the performance on the grid. That's the bottom line of all these pictures that you have here. Okay. Now, one thing that you have to be aware of is that once you reach limits, and as the battery degrade, these services also degrade. Okay. So one has to be aware of that. There are limitations on what you can do with energy storage that have to do with the capacity and have to do with the age. And then we have been looking at what kind of services you can provide with this type of compressed energy storage, flywheels, and battery energy storage to the system. And we have been looking at the ISO. We have been interacting with the ISO. And in that regard, basically, we have been looking at what the ISO and other jurisdictions have been looking at, which is sending frequency regulation signals to the traditional generators, which is what we do now, and energy storage. So splitting that image, that signal. And one of the major challenges we are facing and we have detected is the issue of communication delays, which can be quite significant, okay, for this type of services. So it's not only the fact that they can provide their own service, but also primary frequency regulation, but secondary frequency regulation as well requires some communication with the system, some centralized control. And the communication delays can be quite significant. Okay? So we have been looking at basically what kind of an impact on the system. And the first thing we did, these are the publications we have so far. Okay. We are preparing a paper right now on those, the provision of those services. But the first thing is develop a model, Ontario Power System model of the system. And what we were doing is from measurements versus a very detailed model, a transit stability model of the system, whether we can duplicate the system response. Why? Because based on this, we develop models. And this is the models that we have developed. Okay? So when we looked at the frequency regulation services, we're looking at an approximate model. And the intention of this is basically filter the signal and split it. So first we develop the model. Basically, this is the validation of the model from different perspectives. So so far we have a flywheel and a battery energy storage. Compressed energy storage is being built, the model. And we've been looking at the area control error and how the impact on the system, the regulation signals in AGC. Okay? And we have developed, validated these models, and then we have developed a signal splitting filter in the system, considering time delays, which is what you see here. Okay? And these time delays in the case of Ontario can be up to 4 seconds. So then you start wondering what kind of applications you can have when you split the signal, which is what they do at the PGA&M, slow and fast signal regulation signals, and the impact on the delays on all of this. And this is what you see here. So basically, the bottom line of this is that when you don't have delays and you do have the limited frequency regulation capacity, you do improve the area control area in your system. The frequency regulation improves, which is what you have here. So you have the filter versus the current. So you can see, it's hard to see in this plot, but basically if you look up close, you see that the bottom line, as you can see here in the frequency regulation, is that you are able to provide faster services to the grid. Okay. The problem is that when you introduce delays with these not presented here, the services you can provide are more limited. Okay. Now, we have looked also at the issue of compressed energy storage behind the meter. I guess I'm still within the schedule, which is described in this paper that is going to be presented soon. It's already been accepted and it's going to be presented. I believe it's next week. Yeah, on the application of compressed energy storage. And what was the motivation for this work? Main motivation is that you have industrial customers which are affected by electricity costs. Okay, significant in Ontario. These small size systems, SS stands for small size systems. The idea is what kind of services can you provide in this area? And the idea is to basically provide energy to the system, energy, and especially certain particular energy, because in Ontario, the electricity costs are quite significant. The energy, you have capacity cost and you have energy cost. The energy costs in the system are not significant, but the peak cost or the capacity cost are quite significant. What motivated this work. The other motivation of this work was the fact that, and we worked with a company in Southern Ontario, which there are multiple large industrial facilities in Southern Ontario near these salt caverns that allow you to store air, basically. The idea was how to reduce the power and energy cost of the system, okay, and introduce savings. And this is basically what you see here. So when you look at the peak power, when you use the charging and discharging of the grid, and particularly discharging is what we use in this case. These are the cost of Ontario, hourly Ontario energy cost of prices and the impact on that. And the most important part that we are interested here is the impact on the power on the grid. Okay? As you can see, there are multiple peaks that when you introduce the compressed energy storage system, you basically reduce. And the intention is that this capacity cost, these peak costs, can be significantly affected. And as you can see in the table here, which is what it's trying to summarize, is that the power makes a big difference on the energy in this application, as you would expect. Okay, and past certain power levels, in this case 2 megawatts for this plant, which I believe the peak power is somewhere around, as you can see here in megawatts, the peak power can be all the way up to 20 megawatts. It allows you to basically reduce these 5 peaks, because that's the way the price is computed in Ontario, this capacity price. And as you can see here, the savings can be significant. Okay? And the savings can be such that allows you to justify the introduction of a system which is not cheap, as you can see here. These systems the cost of these systems can be quite significant. Okay? I believe those are the cost to the system. Okay. Then we looked at energy storage, thermal energy storage, a different application of this. This is a paper describing the application of microgrids, in which we were looking at northern communities in Ontario, and in Canada in general, that you are able or you are capable of introducing these basically thermal energy storage systems. Okay, and the intention is to basically regulate frequency or provide services to the system, regulate the variability of energy storage of renewables in your system using these storage mechanism. Okay, and basically what you have is a residential controllable energy storage system, which is basically a demand response, as you can see here. Okay, so that allows you in this system to basically control or interface the system, the introduced renewables. And we looked at an actual community, Casablanca Lake First Nation, which is what you have here. And what happens when you introduce significant, which was the plan at some point, introduce significant amount of renewables. This has changed, by the way. Why? Because they have now built a line, or they are building a line across all these northern communities in Ontario. But nevertheless, when you look at the applications of this is when you don't have a PV plant, and when you have a PV plant and different levels of power levels, which are the different cases we have looked at, with levels of introduction of no thermal energy storage, and 100% thermal energy storage. And you can see that the cost of operation of the microgrid can reduce significantly once you introduce these systems in the residents, in the houses that are connected to this system. Okay? And we have looked at other applications, which is a system in which we have looked at, described in this paper, in which we have looked at a thermal energy system, basically a thermal and electrical energy system where you have combined heat powered boilers, heat pumps, buildings, and water tanks, or this energy storage, and how to make it operate through an energy management system. And we apply these to this particular grid, microgrid lab in Bari, in the Polytechnic of Bari, in which you have wind turbines, you have a PV, and then you have energy storage as well. Battery energy storage, and then you have all these services: boilers, you have thermal energy storage systems, combined heat and power, and a heat pump. And how you make all of these operate within, or play with together. So basically, at the end of the day, with thermal power, you basically regulate the system, make it operate ideally, and reduce the cost. That's the bottom line of this. And for that, you need a region in which you can regulate the frequency. And then we apply these to microgrid as well, from the point of view of looking at electric water heaters, air conditioners, and ground source heat pumps. Okay? So thermostatically controlled. So you have a thermal load of the house, you have an air conditioning model, you have basically a ground source heat pump model, which has two phases, heat and cooling, and the electric water heaters. And we were looking at basically providing frequency regulation services. And this is what you observe here. For this community in the Maya Valley microgrid in British Columbia, sorry about the, because you don't quite clearly see the model. Basically, what you see here is what happens when the frequency in the system where you don't have these services, this particular microgrid, which has basically a single phase, three-phase generator, or single phase grid. So it's an interesting case of study. And you can see that when you have no controls, when you introduce electric water heaters, different type of controls, how you improve as you go along. This is with the air conditioning, and finally with the ground source heat pump. And as you can see here is that once you introduce these energy storage services, these thermal energy storage services of different levels, you are able to now bring the frequency within the norm. Okay. Allow for this particular system. That's the bottom line of this. And then we moved on to providing ancillary services using ground source heat pump, GSHP, to the system. Now, not only to a microgrid, but to a large system. Now we need a load aggregator. So in which you have these ground source heat pumps basically aggregated and providing the coordinated services to the system. So you have a price taker aggregator. This is the model we have looked at, describing this paper that will be presented at the general meeting coming up in August. And the idea is, with different models, we compare what happens with the system, the base case system, in which you basically are trying to just regulate temperature, keeping a minimal deviation, or basically providing a services to the grid in two levels, the day ahead and the real-time mode. Okay, so basically with all the constraints that you have in your system, from the load aggregator point of view, this is a load aggregator basically, and how they can benefit from the system. And basically what you see here is that with respect to the base case, you can have with HVAC or ground source heat pump, you can introduce services. You can provide services using the energy storage in the case of the ground source heat pump or the HVAC system in the system. So you can see the savings that you can accrue to the system that can be a benefit for the aggregator and justify this participation. And we have looked also at the issue of uncertainties, which is the work we're doing right now, okay, to maximize profit from the investor perspective. So you have a CAC system that is providing services to the network. It's a price taker at this point. So, and the intention is, well, how would you optimally operate this CAS system, considering the uncertainties, okay, in the system? So we're looking at two models, ROS optimization and a finite method. So, and we're looking at trying to look at what the relationship of these two are. And this is a paper that will be basically what we have prepared. We're preparing a paper to, well, this is going to be presented to the general meeting, I guess, for next year, or maybe before we find another proper place to present this. We don't have a lot of time, but let me describe briefly the mathematical model. The objective is basically to consider revenue and operational cost of your facilities to maximize profit. Okay, so subject to the constraints, the physical constraints of your system. Okay? And you need to consider price uncertainties from the point of view of the operator. And basically, this is what happens when you consider price uncertainties in the system with different levels of uncertainty and different levels of protection. Well, this is deterministic, and this is the maximum uncertainty you can consider in a 24-hour model. So the deviations of your system using a robust optimization model, where you have these two parameters to play with, and here you see the results. This is what happens with the profit as a protection against uncertainty increases. As you would expect, the profit goes down as more uncertainties in the prices take place. And here's the comparison of what happens when you have a deterministic model versus Monte Carlo versus a Monte Carlo model, which is basically a benchmark for our system. This is Monte Carlo for different levels of uncertainty, and this is the deterministic model. Okay? And you can see here the impact of robust optimization on the profit of the system. And finally, to close my presentation within the allotted time. Yep, I still have 5 minutes to go since we started about 5 minutes late. These are the paper. We have basically looked at the issue of what happens when we looked at this hybrid power flow control, which I'm going to describe in a second. So the intention is to eventually introduce energy storage into a system that basically looks like this, which is basically a UPFC, and the services you can provide with them. And basically, it's a system that allows you to, like the UPFC, to have different modes of control, okay? Which basically allows you to control the power flowing through this line, and also provide voltage regulation services, okay? And we have looked at applications of in the Ontario system, and adding this as a reduced model of the Ontario system, providing services to that network, congestion services, basically, and this is what you have in terms of savings. Okay? The savings as a point of maximal benefit versus basically the size of your HPFC. So this has been described in a paper already. The papers are listed here. And the application of distribution system grids, which is where we are focusing on. So how you can use this as an intelligent switch that allows you to, in this case, provide these services where you have a solar power generation in your system. Okay? And this is basically a power quality type of services, voltage dips in the grid. So what we're doing next, well, I guess it's not here described, but what we're doing next, within my 45 minutes allotted, what we're doing next is what happens if we use this to interface the grid. So we have the grid now. We have a microgrid now. And we're using this HPFC system with energy storage. We're looking at the issue of energy storage in this system to connect to the grid. Okay? And we have this interface, which will allow you to have an intelligent switch versus a AC/DC AC converter. Okay? And the kind of services, and we're writing a paper on that. And because the intention of this compared to a UPFC or other applications, so a UPFC is basically an AC/DC AC converter interface, is the cost. It's 1/3 of the cost. So this system that you have here is 1/3 of the cost of the UPFC or alternative technologies like AC/DC AC converter. Okay. So with that, within the 45 minutes, I cover all these different aspects, and now I welcome any questions.
Thank you, Claudio.
Thank you.
Exhaustive presentation. I have several questions from the audience and some of my own. So first questions from the audience is from Marcos Cruz, and he's asking, Professor, do you have any comments on the type of the batteries that we will see in the future of electric vehicles? It's a little bit out of the topic of yours, but maybe you have an answer.
Sure. We have not looked at the specific technologies of electric vehicle applications. We have looked at electric vehicle interfaces with the grid and how you can control and regulate, basically allow more connections to the grid, but we have not looked at the technologies themselves. What we are looking at, though, is the second, what do you call it? I'm looking for the word. When you can recycle these batteries and provide this type of services that I have described here. Okay, but we're just looking at lithium ion. Okay, if I may jump to that, just a second. Sorry about this. Maybe I shouldn't be doing this, but this type of services, right?
Okay, so do you think that second life batteries will play an important role in this battery energy storage?
Basically, the type of applications we're looking at, sorry about this, I'm trying to look for the slides. If you allow me a second, this type of service. We believe that electric vehicles, once you allow V2G, voltage to grid services, you should be able to provide this type of services to the grid using electric vehicles. So that's the kind of application we envision for these type of models that we are developing.
Okay, thank you. Next question is from Hadi Habib. Do you think that compressed air storage has a better future from the market point of view for grid scale and microgrid scale? So
for grid scale, yeah, thank you. Yeah, I think that for grid scale applications, this is the kind of services you can provide. Okay. Sorry, it's over here. This is the kind of services you can provide, and I think it has a lot of potential. However, one caveat here is the fact of this: you need to have, for this to make sense, you need a proper cavern storage in the system. So in other words, you are not going to have these services anywhere. We have looked at the issue of providing these through basically tanks in a microgrid, but they are not competitive compared to the battery energy storage services you can provide to the system in a microgrid context, because it requires very specific. It's costly compared to what you can do when you have a battery. However, for grid level services, this is a very good option if you have this alternative. If you have a cavern available for you, which is the case of the example I provided here for compressed energy storage behind the grid, behind the meter. Okay, this is an example in which you can see that if you have the cavern availability, you can certainly provide services and especially savings for the customer on the other side of the meter.
Okay, the next two questions are from Jounès from Artois University from France. First one is, what about solid state hydrogen energy storage? And can we say that it will be a solution for the near future? So
okay, that's a good question. We have not looked much at hydrogen. We looked at the hydrogen issue from the perspective of the standard technology that you have here, right? We have not looked at solid hydrogen. But what we found is that we presented several studies on this technology. Okay? We have an electrolyzer and a system for grid services. This did not make a lot of sense compared to batteries. The problem that we had, this was very good for seasonal storage. Hydrogen was very good for, and it's been proven in microgrid examples. In the Vela Cool example in British Columbia, in which they have shown that this type of storage for seasonal purposes makes a lot of sense, because you can store hydrogen, significant amounts of hydrogen, going from one season, the summer, to the winter, basically. However, when we looked at the application of interfacing this with wind, to try to use basically the energy that is not being used by the wind turbines to store hydrogen, it did not make a lot of commercial sense, unless you use the hydrogen for other purposes. So, for example, to fuel vehicles, or for industrial type of applications. in which case hydrogen didn't make sense. But we only looked at hydrogen as a gas.
Okay. Next question is from the same journalist from Waterloo University from France. What is the effects on the advantage of the DC grid on energy storage?
Well, that's an interesting question. It depends on the kind of loads that you have in the system. I guess you're talking about basically interfacing at this level, basically having your grid, right? And in that case, I guess when you have a DC grid system, which are being developed and are growing more and more, I guess it makes sense to have to use these interfaces for coupling the energy storage to your system, right? And whenever you have these type of services, it makes sense. Now, whether that would be applied, it could apply to any of these, by the way, where you have a DC link in the system. Okay? So that it really depends on the type of energy storage you have. For example, in compressed energy storage, you wouldn't have that option. Okay? So that's all I can say with regard to that particular topic. Yeah.
Peter Palensky, wouldn't flywheel be the one-fits-all solution? Can be used anywhere, no toxic chemicals, available in any size, proven technology, old-fashioned inertia. So what about flywheel? Is it not really the solution for fits it all?
Well, flywheel has a problem with energy. It's energy limited. Okay. You do have, I agree. I mean, you have all these advantages: a long life, high power, energy density, fast charging and discharging, environmentally friendly. Although there's an issue of losses, which is being brought up to our attention in another project we are involved in. However, I mean, if you keep this idle, you lose energy. But however, it has many advantages, and I agree. The problem is that you don't have a lot of energy capacity, because that will require a huge flywheel to be able to store energy for hours, right? Minus 2 hours. But for the services that it provides for fast frequency regulation services, it's ideal. I agree. I mean, it's one of the best options you may have for certain applications. Yes.
Next question from Peter Palensky. How do you think we should organize coordination of storage operations if we assume different ownership of distributed batteries, etc.? How to reach consensus in very short time?
Well, that's an interesting question, and that goes to the problem of this type of problem you have here. Would this be feasible? Because you have different battery energy storage services. For example, in this example, it could be other services, other technologies, and the issue is, okay, so how could you? Here we're assuming that everything is perfect and we can coordinate all these services. Now, in practice, that's a big if. Because when you have a system like this in which you have different owners and different objectives, the only way I can see this happening is when you have an incentive program, when you are going to basically pay good money for these services. So these batteries can be basically motivated, which is going back to this transactive energy type of models in which you basically are providing a service and getting a benefit from it. And that's a big if. Are we going to be able to do that? And I think in the context of actual applications, it will have to be to some sort of market model that allows you to do this. The technology we believe is feasible. You can coordinate these systems and make them work together. Now, making it happen, I think that's a major challenge, and I think that will require a market. New market structure, new market ideas that allow you to do this. And in that context, there's a lot of work in transactive energy type of markets in which you're going to be basically paid for your services in a way that makes it enticing to do this. And we have had a lot of experience with this type of consumers providing services to the grid. And unless you pay them for the service significantly, they will basically have no interest on doing this.
Okay, next question is related. When it will become feasible to have the same level of frequency stability provided by battery energy storage, virtual inertia, as it is achieved by the big synchronous generators? Will it be ever feasible?
Well, there's an example of this already. Microgrids, you already have 100%. You have many examples of 100% penetration of systems without no inertia, right? So it is feasible. I think that's a question now that's being addressed at the microgrid level. Now, the transmission system level, there are different challenges. One of them is, for example, interconnections. The grid itself plays a role in all of this. That your response, there's no immediate response of your system when you have, in other words, you have a localized, which is the example I have here. The example you have here, in which the energy storage service can provide services, local services, very well. But when you interconnect them to the grid, all these communication delays might basically hinder the application of energy storage in terms of the services they can provide. So I think they will. It's feasible. It's been demonstrated in microgrids. Now there are certain issues that need to be addressed. And in the studies we're doing right now, we believe that the energy storage, the best way of handling energy storage is not as much for this type of services of secondary frequency regulation in a transmission system, because of the communication delays, which basically limit your application. Also, the size is another problem, but nevertheless, if you have enough size, you should be able to provide the services. But for primary frequency regulation, so local frequency regulation, we believe that they will be ideal for that kind of service. We are still working on that, but this is the way we're going because of these issues of communication delays.
Okay, I have several questions of my own, but I see one more question coming from Younes from Artois University from France. We know that the temperature has a big effect on energy storage. What is the solution, especially in the Sahara region, for example, in Africa or Middle East?
That's a good question. I don't have an answer to that because we haven't worked on that particular problem of the energy storage technology itself. Our focus has been mostly on the interface and modeling and interaction with the grid. So don't really have an answer. That's a good question. I guess it's an issue for a question for energy storage technology developers and researchers, that how can you manage heat properly in the system. However, there are applications in which they have been demonstrated to work, right? In cold climates, they can be very good, because there's another challenge. In cold climates, energy storage systems they require certain temperature of operations. That you have exactly the opposite problem, is the thermal management of the battery, in the sense that it doesn't freeze. And that issues have been addressed with packaging, etc. Now, in applications of in hot areas, I have not looked at, and I cannot really provide an answer to that.
Thank you. I have a next question from Peter Palensky. I know the answer, but still I ask you, should we get rid of AC in order to eliminate 80% of our problems in the grid, such as stability, generator coherency, etc.?
Well, be careful with DC grids have their own stability problems, eh? So we cannot say that DC grids are going to be the solution for everything. I believe that they're an option. I guess you don't have the reactive power problems, the frequency regulation problems. So that's a big advantage. However, there's a major challenge and that we need to be aware of, and that's the issue of sunk cost, right? You already have an AC system worth trillions of dollars, which you cannot simply ignore. As you move forward, which is what is happening in the smaller applications, DC systems are certainly an option and a solution. They have their own stability problems, so that you have to deal with, but certainly there is not an answer for all. But I think there will the type of problems you have to deal with that are going to be different. Whether they are more challenging or less challenging, that's still to be debated. But certainly, at the end of the day, the way I envision this is that system in which you're going to have both systems operating in parallel, in some way, interacting in some way or form.
Okay, I have two more open questions for myself. In Europe, we are busy with energy transition, and part of that is electrification of society. We are even considering heating with electricity in the future. And all the scenarios are showing that the grid has to be strengthened even 3 to 5 times because of the PV, because of the electric vehicles, because of the heating, etc. The other option is installing a lot of storage in the grid. do you think it will be feasible solution to install storage instead of installing more cables and transformers?
Well, energy storage, I mean, I guess you cannot get away from the fact that at some point to add all these, this is happening in Canada as well, right? There's a lot of, in Ontario, for example, we're trying to move our system, thermal system from a gas-based residential to electric, what is happening in British Columbia, in Quebec, where they are basically hydro systems in which their heating is basically coming from, this is an example, heating is coming from electrical systems. In Ontario, on the other hand, we have had these gas systems. So, however, with all these additional power we have available, there's intention of moving the heating systems into electrical. Now, in this context, I guess the thermal energy storage of houses, etc., can be taking advantage of it, water heating, etc., which is not being done, or district heating, for example, which is a discussion here, which already has happened in Europe. It's another option, right? So I think that there are options, energy storage options. It's not only batteries, but you can also look at thermal that will help in this process. But eventually, you're going to have to invest on bigger lines. In our case, no more generation because we have plenty in Ontario, but certainly upgrades of the distribution system, because you can go with intelligence so far. For example, work we have done in electric vehicles is, well, how can you defer investments, not eliminate them, but defer investments by intelligently charging vehicles, right? But there's so far you can go. Once you have 100% penetration, that won't cut it, right? So you're gonna have to basically, with energy storage in the picture, eventually you're going to have to invest on upgrading your systems in the long run. But if you want to make an electrify the grid, electrify the transportation system, electrify the heating systems, the energy systems in general, yeah, we're going to have investments at some point. But energy storage can play a role in the deferrals, right, to a certain degree.
You introduced flywheel, compressed air, battery energy storage, thermal storage, combined heat power for different applications. Every time you used a different example in your presentation. So which of these storage has potential to really work as a strengthening of the grid and fulfilling these functions on the short and the long term? What is the potential of the storage options in this application?
Well, I think all of them can play a role. They all have limitations. They all have advantages. For example, compressed energy storage is a good example of an application in which you can use it only in certain areas, right? But in those areas where you have the option to store, or cheap options to store air, they are ideal. They are really competitive in terms of cost. In terms of performance, they can really provide good services. Now, it really depends on the application you have. Battery energy storage also have their own niche and applications. For example, the example I have here, we are right in front of us. Energy storage, battery energy storage is not the best. Okay, when you have these not for secondary frequency regulation type of applications in grids. So it really depends. I guess there's no. I don't think there's a silver bullet here. I would argue that you can use all these technologies combined. That would be the idea, right? Mix energies, thermal energy storage with battery, with if you have availability of storage for air, compressed energy storage, and making them all work together. Okay, that would be my answer.
Okay, I have two more questions. One is from Younes from Artois University from France. Can artificial intelligence be a big issue in energy storage management?
Yeah, I believe so. In fact, in this one of the applications we're looking at, or one of the modeling applications we're looking at, is for these aggregator models. Is basically AI. How can we model these or come up with aggregated models that allows us to basically harness the benefit or demonstrate the benefit of these aggregated systems? So in this example, for example, we have developed for aggregated model, we have developed neural network based. That was the only option, by the way, a black box model of the systems. We could not do it with other type of applications. So that's an example. Other examples is basically in the issue of control, right? distributed controls in which AI can play a very interesting role, especially when you have these cyber physical systems and data analytics that are getting sort of mixed now. When you have a system like this, you're going to have a challenge of having a lot of data in your system, right? So how can you harness the benefit of that? Or how can you harness this for modeling, for control? And I think that the AI will play a significant role. Yes, in that context.
Thank you. And I have very last question from myself. We spend a lot of money to keep the grid reliable, and we have the N-1 contingency. But if we have a lot of storage in the grid, we can completely rethink about the reliability of the grid and about N-1 contingency. Do you agree with this statement?
Well, that's an interesting question. And this has to go with, for example, how reliable microgrids are. Let me give you an example. What is happening in Northern Ontario here? These are basically microgrid systems I have operated. The same happens in other applications. In Chile, for example, I've noticed this. They have the problem of reliability, right? And in the case of Ontario, what is happening is Northern Ontario, we're moving from a microgrid system which is basically also can include microgrids are basically very good applications for any energy storage, in which you can move from an energy system, we have a microgrid, into an energy system in which you are connected to the grid. In the case of Chile, it's the reverse. You have an unreliable AC service, and now you're adding a microgrid on the other side so you can have a reliable service, which is what is happening in North America. These applications of energy storage, in particular, in the context of microgrids, is for reliability purposes, right? Now, moving away from the N-1, that's an interesting question. I mean, depends on how willing you are to take risk, right? And pay the price for it. If you have a microgrid in your own, you have a grid here. If I had a generator in my house, solar and could be solar panel and battery energy storage, I would not be as reliable on the grid as other people who don't have access to that. Now, the issue is cost, okay? Do I have the money to do that? That allows me to basically have 100% reliability in my system. So if the grid fails, which is happened here in Ontario, in Toronto a few years back, when you have we had an ice storm, and what happened is that subdivisions, basically neighborhoods in Toronto, were basically, oh, hopefully you can hear me. I'm having network problems here. Basically, what happened is that they were without electricity for 2 weeks. So in that context, sure, microgrids and battery energy storage play a role. It can play a role as long as the cost is justifiable. I guess as all these costs go down, that could be something that, yeah, could be rethought. But I don't see that happening anytime soon, yeah.
So thank you, Claudio. Ladies and gentlemen, let's give Claudio a big hand.
Thank you.
Thank
you, everybody.
Present for you. We will send it to your home. We hope to see you in Delft, but of course circumstances don't allow us to have this conference on the normal way. Anyway, your present will be sent. Ladies and gentlemen, I invite you to join the sessions starting at 14:30 in 20 minutes at the addresses which are on the internet site of the ISIE conference. Let me thank again to Claudio, and
thank you, Bob.
Enjoy the rest of the conference. Thank you.
Thank you. Bye now. Bye for now. Bye now.